So once again, I welcoming you all for this second part of the sequential circuit, that is latch. In the last part, we have discussed a fundamental latches by using the SR flip-flops or SR latch. Now, the same thing I'm going to explain with the enable pin, with the enable pin. So you know what is meant by latch from the earlier class definition or earlier class discussion. So the SR latch or a latch is a unit which is used as a memory, that is also a temporary memory. It has two inputs and two outputs. Inputs are R and S. S means set, R means reset. S means set, R means reset, and Q and Q bar are in sometimes Q1 Qn plus 1, like that. So that and all we have discussed in the earlier session. Now I am entering into the SR flip flop with latch enable. So the last session we have discussed in the SR latch without enable pin. That means this particular part already we have discussed. Now I'm entering into this. So this is the SR flip flop or latch. This is the SR flip flop or a latch. It has two inputs S and R and two outputs Q and Q bar or Q and Qn plus 1. So just like this. So Q and Qn plus 1. So we are going to realize the operation of SR flip-flops by using this truth table R. The exact meaning is what? Whenever I am giving the different combinations of inputs to the S and R terminals, that is input terminals here. That is input terminals here. What is the response? What is the response? That is outputs we are going to discuss now. That's all. So in this case, the enable pin is available here. The pin is called enable pin, which is available here. So enable means to make the enable, or it gives a permission to the circuit or a device or a system. Whenever this pin is enabled, it works properly. Otherwise, it will not work, or it gives a connection to the other part. Otherwise, it will not connect. Okay. So according to that fundamental, so we are going to discussing this enable pin. So here, this SR latch or a flip flop is designed with NAND gate. But in the earlier case, the SR latch or flip flop discussed with NOR logic gates. But here it is designed by using the NAND gate. So for that, you should thorough or strong about the truth table of a NAND gate. So according to the truth tables of a NAND gate, if any one of the input equal to 0, output will be 1. Or all the inputs are 1, output will be 0. That's all. So with this fundamental, I'm entering into the SR logic latch, that is SR flip-flop. This is a construction of SR flip-flop. This is the construction of a SR flip-flop. It has two inputs S and R along with the enable pin or enable terminal, and then Q and Q bar, which are cross connected with each other, which are cross connected with each other. That means the Q output is given to the one of the input of this logic gate, and Q bar output is given to the one of the input of this one. So this is very important. Now what we are going to discussing, if suppose I assumed like this, if suppose I am assuming my enable pin equal to 0, what will happen? So since enable is 0 means one of the inputs of these two gates are 0. These two gates are now 0. Say for example, it may be a N1, NAND 1, and this may be NAND gate 2. Like that you can name it, no problem. Since you are a beginner, you can named this as a N1, N2 and N3. This is the third NAND gate and this is a fourth NAND gate. Fourth NAND gate. Okay. Okay. Then since my enable input is equal to 0, one of the input of each NAND gates is 0. So I already mentioned to you, or you aware about that the definition for NAND gate based upon the truth table, any one of the input equal to 0 means output will be 1. Output will be 1. Therefore, what will happen? One of the input of these two gates is now 1 1. Is now 1 1. Now, initially by assuming my Q input equal to 0, hence Q bar equal to 1. Hence Q bar equal to 1. No doubt about this. Okay. Since it is 0, it is 1. Okay. Because of the assumption we made here, the Q equal to 0, that 0 comes to here. That 0 comes to here. Please listen carefully. That 0 comes to here. Since one of the input equal to 0, my output equal to 1. This 1 is given to the one of the input of my N3, that means NAND gate 3. Then you check the inputs, all the inputs are 1 now, hence the output equal to 0. This is the first condition. Okay, now I'm considering the initial condition as 1 instead of 0, that means Q, hence it is 0. My Q bar equal to 0. Please listen, I am assuming that the second condition, my Q output equal to 1, hence the Q bar equal to 0. Hence the Q bar equal to 0. Since this Q bar equal to 0, it comes to here, it comes to here now. What will happen? One of the input of my N3 equal to 0, therefore the output equal to 1. Therefore the output equal to 1. Here you please listen carefully. So I made the assumption my Q output equal to 1, hence Q bar equal to 0. So this Q bar is given to the input of this NAND gate N3. So that makes my Q output equal to 1. So what assumption I made, that assumption is retained here. Since it is 1, so it comes to here, it comes to here. What will happen? Both inputs are now 1, output will be 0. Therefore, it satisfied the conditions we initially assumed. So it shows what? In the previous assumption, here I am considering my Q as 0, hence Q bar equal to 1. Then after tracing the operation, it gives the same output. Similarly, I'm going to check, instead of 0 as my Q output, I'm taking my Q output equal to 1, hence Q bar equal to 0. This 0 is connected to the one of the input of this AND gate, NAND gate N3, hence it makes the output equal to 1. That makes this NAND gate 4 output equal to 0. So whatever may be the assumption here, whenever my enable pin equal to 0, there is no changes in output. I think now you can get the clear idea about this. So if you understand this, that's all the subject. Now my output is no change. My output is no change condition. Okay. Whenever my input equal to, enable pin is equal to 0. Okay. Similarly, you can verify all the conditions. Now the condition checked by using this circuit is 0 0 and 0 1 0 1. That means my S and R input equal to 0 0 0 0 to be checked. But here the logic circuit is having the enable pin equal to 0. Therefore it makes whatever may be the combinations of your input. Please listen here, it is very very important thing. Why? If suppose my S input equal to 0, R input is also 0, already one of the input of N1 and N2 equal to 0, hence it produces the output as 1 1. Since it is 1 1, what will happen? Whatever be the assumptions you made, the same thing only retained here. Okay, then even if it is 1 0 or 0 1 or 1 1. Please understand this, it is very important thing. Say for example, the last assumption I made, or the input is 1 1 now. So here it comes as a 1 and 1. Because of my enable input equal to 0, one of the input of my n1 and n2 is 0. So because of this, my output is again 1 1. Then if you made whatever may be the q output, it will be a no changing output. It will be a no changing output. That's all. So with this, I finish the enable pin as 0. What is the changes in its output? Now, the assumption made, instead of 0, please listen, instead of 0, I'm going to consider my enable pin as a 1. So please listen carefully. It is very important. If you understand this, that's all other flip-flops are latches. So since my enable input equal to 1, hence n1 and n2, n3, n4 like that. Here also you can please named, because we are in the beginning stage, so it will be very useful to you, and also at the time of writing the examination it may be very useful to you. Okay, so since the enable pin is equal to 1, one of the inputs of my n1 and n2 gates are 1 1. Okay, but in the earlier case, enable pin equal to 0, so one of the inputs of n1 and n2 equal to 0, so that makes the outputs of these two gates is equal to 1 1. Now it is not possible, so the output is now depends on the SR input. Now I'm going to check this condition. I'm going to check this condition. Please listen carefully. The first one, now I'm assuming my S input equal to 0. That means this condition. Okay, that means this condition. Okay, or this condition, both are same. That means this condition, S equal to 0 or equal to 0. Please listen carefully. S input equal to 0 or equal to 0, enable equal to 1. So at the time of your examination, you can write like this: enable pin equal to what, S input equal to what, or input equal to what. That's enough, no need of writing any paragraph. Okay, since one of the input now 0, output will be 1. Output will be 1 1 here. So according to the earlier discussion, since it is 1 1, whatever the assumption we made here, whatever the assumption we made here, that means q equal to 0 means automatically q bar equal to 1. The same thing will be retained here. Will be retained here. How? So one of the input of n3 and n4 equal to 1. Since I made the assumption of q equal to 0, that comes to here. What will happen? This makes the output as 1 here, 1 here. This one is again connected to here. Now both the inputs of n3 equal to 1, hence output equal to 0. So it retains the output as it is. Suppose I would like to take, instead of 0, 1 as a q output. What will happen? My q bar will be automatically 0. So this 0 now comes to here. That is my n3 input, one of the input equal to 0. That makes my output equal to 1, because one of the input of n3 equal to 0. So that makes 1 as a output. That one comes to here. Now the both the input of this NAND gate equal to 1, hence it makes a 0. So it gives a clear picture about whatever the assumption I made, the same thing will be retained. So I can say this is a no changing condition. No changing condition. Okay, that's all. The first operation is over. So initially S equal to 0, R equal to 0, then first condition my q equal to 0, hence q bar equal to 1, and my q equal to 1, hence a q bar equal to 0. Therefore there is no changes. Therefore there is no changes. Okay, and then now second part. Now I am going to take the second assumption. That means here. That means here. So with enable pin as a 1, enable pin as a 1, hence one of the input of each NAND gate equal to 1. Now I made my S input as a 0, R input as 1 here, R input as 1. Okay, then now initially I made my Q equal to 0, hence Q bar equal to 1. Please listen, it is very important. Okay, so Q equal to 0 and Q bar equal to 1. Now you check all the gates inputs. N1 gates, one of the input equal to 0 here, hence the output equal to 1. All the inputs of this NAND gate equal to 1, therefore output will be 0. Okay, then straight away we can write here one of the input equal to 0 for this N4, so my output will be 1. That 1 comes to here. Now both the inputs of this NAND gate is equal to 1, hence output equal to 0. Okay, so initially I made 0 as a Q output and hence Q bar equal to 1. Now for the same condition, please listen carefully. I'm going to assume my Q equal to 1 now. My Q equal to 1 now. So instead of 0, I assumed that my Q equal to 1. Hence Q bar equal to 0. Okay. What will happen? So here same conditions. My S equal to 0, R equal to 1. So that gives here as a 1, 0. Since, please listen, since the output of this one equal to 0, that makes this 0 as 1. That makes this 0 as 1. This 1 now comes to here. So that 1 now comes to here. Therefore, all the applied inputs of my N3 equal to 1. Hence, my output is changing into 0 for my second assumption. Please listen carefully in this particular case. What will happen? Whatever may be the assumption I made here, either Q equal to 0 or Q equal to 1, what will be the final result I obtained after tracing the output? 0, 0. That makes this condition reset my output, or reset my flip flops, or reset my latch is now in reset position. Okay, that's all. Similarly, I'm going to explain the third condition. That means this part we are going to discussing now. My enable part pin is equal to 1, hence one of the input equal to 1. You can parallelly analyzing or tracing the operation, no problem. Otherwise you please listen carefully. So since enable pin equal to 1, one of the inputs of my N1 and N2 equal to 1, now my S input equal to, that means here set input is equal to 1 and reset input equal to 0. Okay, since one of the input equal to 0, my output will be 1. Here both the inputs are 1, my output will be 0 according to the truth table of NAND gate. Okay, now please listen carefully. Now I made the assumption initially my Q equal to 0. First condition, my Q equal to 0, hence Q bar equal to 1. Okay, now since the conditions applied here, S equal to 1, R equal to 0, the output of my N1 equal to 0, that makes this logic gate output equal to 1. Why? One of the input equal to 0. Please listen carefully. This is very important thing. Opposite to the previous state. So 0 is given as input of this N3, that makes the output equal to 1 here. Okay, that 1 comes to here. All the inputs are 1 now, hence it changes this into 0. Okay, then for the same input condition, I made the assumption is like this. Instead of 0, now I assume this is a 1. Hence it is 0. Okay, hence it is 0. So hence a Q bar output equal to 0. Now I am tracing the output. Since one of the input of this AND gate equal to 0, the output equal to 1. My output equal to 1. That 1 comes to here. Now both the inputs of this NAND gate equal to 1, hence my output equal to 0. So now you listen or see carefully here, whatever may be the assumption I made, my Q output is always 1. So we called this particular operation or this thing is called setting of my flip flops. So setting flip flop. In the earlier case, it is called a resetting operation. Before to that, that operation is called no change. That means whatever may be the assumption made, that retains as it is in the first case. In the first case. But in the second case, whatever may be the assumption made here, either my Q equal to 0 or 1, finally it reset the value. That means Q output equal to 0. Hence Q bar equal to 1. Similarly, in the third operation, I take my input as S equal to 1 and R equal to 0 along with my enable pin as a 1. What will happen? Whatever the assumption I made, that means the previous or earlier state, Q equal to 0 or Q equal to 1, it sets as a 1 as the output. So it makes setting operation. So this is called set. Okay. Then now I'm moving into the last part of this operation. Again, I retain the same thing. I retain the same thing. My enable pin now also 1. Hence, one of the input equal to 1 here. That means N1 and N2. Now, my S input is also 1. R input is also 1. Please listen. Because of the truth table, this and NAND gate output equal to 0 because all the inputs are 1. Similarly, here also 0. Okay. Now, one of the input equal to 0, output will be 1. Here also the 1. So, it is not possible. So, we called this as a forbidden level. So, we called this as a forbidden or indeterminate level in some authors. In some authors. Say, for example, whatever may be the assumption, if I made my Q equal to 0 or 1, okay, since it is 0 means 1, 1 means 0. Whatever may be the assumption I made, no problem because what will be the result? One of the input equal to 0 for both the gates, that makes this as a forbidden level. There is no possibilities. That means it cannot give any changes. Okay. So this is the SR flip-flops operation. This is the SR flip-flop operation. So the entire operation is tabulated here. The entire operation of the SR flip-flop is tabulated here. That means initially I made the assumption is my S input and R input is 0, 0 means 0, 0 means what will happen? There is no changes in the output. There is no changes in the output. Whatever may be the assumption we made, Q equal to 0 means here also 0. Here 1 means here also 1. Okay, that's all. So the present state now and the next state, like that you assumed. Otherwise, you please trace the operation. Then the second case, if you make the assumption as like this, 0 and 1, 0 and 1 combinations along with my enable equal to 1, along with my enable pin is equal to 1. What will happen? It reset the output. That means my Q output equal to 0. Whatever may be the assumption you made, that makes my Q output as 0. So we called this as a resetting operation. Then in my third case or a third assumption or a third operation, what will happen? I assumed that my S input equal to 1, R input equal to 0, along with E equal to 1. These are all only possible when enable input is equal to 1. This is very important thing. Okay, all are possible only under this condition. Now it produces the output equal to like this 1 1. That means it sets the output. It sets the output. What is meant by setting here? That means my Q output is 1. My Q output is equal to 1. And then the final operation or a set of input is 1 1 along with my enable, what will happen? That makes my output equal to forbidden or indeterminate. We cannot determine whatever may be the assumption, either q equal to 0 or 1, whatever may be the thing, we cannot determine, because one of the input of n3 and n4 is always 0 or already 0, hence that makes output is indeterminate. So with this SR flip-flop operation is over. Next part we are going to discussing about the different logic latches or flip-flops and triggering techniques.